everybody, it's Mrs. Dunn. What I want to do in this screencast is talk to you about infinite sets. So what we're going to learn specifically is how to show a set is infinite by placing it in a one-to-one correspondence with a proper subset of itself. And we're going to show that a set has cardinal number aleph null. The idea behind this whole screencast, the idea behind this whole section, is answering this type of question. Which of these sets is larger? So on the left side of the screen, you have the set of natural numbers, which are sometimes called the counting numbers, which are the numbers 1, 2, 3, etc. On the right side, you have the set of odd numbers, 1, 3, 5. So both of those sets are infinite. We learned about that in the first section of this chapter. But which of these is bigger? Which of these is larger? That's the question we're going to answer in this screencast. So George Cantor is a famous mathematician. Maybe one of you are researching him for your project. But George Cantor defines an infinite set this way. An infinite set is a set that can be placed in a one-to-one correspondence with a proper subset of itself. Remember that idea of proper subset means that while every element of the subset is in the original set, the subset and the original set are not allowed to be equal to each other. So first of all, I want to show you what a one-to-one correspondence looks like. So if we have this set A, which contains the pound sign, the question mark, and the and sign, we can set up a one-to-one correspondence with set B, which are the elements 1, 2, and 3. That just means every element in A gets paired up with an element in B. That's what a one-to-one correspondence looks like. So suppose we're asked to show that the set of natural numbers is an infinite set. Then what we need to do is I'm going to come back to that screen, we need to establish a one-to-one correspondence between the counting numbers, or the natural numbers here, and a proper subset of the natural numbers. So in this previous screen, I was talking about this element n. N is called the general term of the set. And it's the general term of this set of natural numbers or counting numbers. So for the general term, it's not always going to be n, but n is used in it. When we substitute 1 for n, we should get the first element of that set. So in here, it's pretty obvious. When I plug in a 1 for n, I get 1, and that's the first element of this set. But it's going to come up later in our discussions. Okay, so remember, we're going to establish a one-to-one correspondence between the natural numbers or counting numbers and a proper subset of those natural numbers. Well, a proper subset can't be equal. So let's suppose we just forget about 1 and we set up a one-to-one correspondence between the elements 1, 2, 3, etc. and 2, 3, 4, etc. Look at this on the next screen. So all I did was drop out the element 1. So now I have a proper subset because these are not equal to each other. But we do notice that we have a one-to-one correspondence. So the first element in n is 1. The first element in A is 2. And we can make a one-to-one correspondence. The pairing of the general terms is really important. Remember, when I plug in 1, I get 1, the first element of that set. When I plug in 1 for n here, I get 2, which is the first element of set A. Because every element in n is paired with an element in A, we have now shown that n is n is an infinite set. A is a proper subset of n, and we have paired every term in n with A. So therefore, n must be infinite. Let's do it with a different set. It's a little bit more complicated. So for example, we have this set of numbers 6, 11, 16, 21, and 26. This pattern is going to go on forever. Remember, or you should notice you're adding 5 to each one of these terms to get the next term. So the next term would be 31, 36, 41, 46, etc. So this set is infinite. We know that. We look at that. We can see it's infinite. But to prove it, we have to place it in a one-to-one correspondence with itself. Now, a lot of students have trouble with that general term. So the general term here is 5n plus 1. Let me give you a little help on how I got that. What's the difference between each of these terms? 6 plus 5 is 11, 11 plus 5 is 16. I mentioned that before. So the general term is going to be 5n, and then we're going to add or subtract some number to get the term. So for example, remember, if I plug in 1 for n, I'd have 5 times 1 is 5. I added 1 because 5 times 1 is 5, and 5 plus 1 gives me the next term. So 5n plus 1 is the general term. Notice, if I plug in 2, 5 times 2 is 10, plus 1 is 11. If I plug in 3, 5 times 3 is 15, plus 1 is 16. That's why the general term is 5n plus 1. So look at the pairing. So to pair n with a proper subset of itself, A, I am pairing it with every element is paired up. Notice this is a subset because it doesn't include 6, but 6 is paired up with 11, 11 is paired up with 6, one-to-one correspondence here. And the one-to-one correspondence of the general terms is what we're looking for. So the general term established in the previous screen was 5n plus 1. If I plug in 1, I get 6. If I plug in 2, I get 11. If I plug in 3, I get 16. And down here, the general term is 5n plus 6. If I plug in 1, I get 5 plus 6, which is 11. If I plug in 2, 10 plus 6 is 16. If I plug in 3, 15 plus 6 is 21, etc. So there you go. We've proved that this set, 6, 11, 16, etc., is an infinite set. Okay, so now let's talk about this idea of this Aleph Null. Okay. So look at these two sets, those sets that I brought up before. We have set A, which has 3 elements in it. So we say the cardinal number of A is 3. And the cardinal number of B is 3. That's the same as counting the number of elements in each of the sets. So any set that can be placed in a one-to-one correspondence with the set of natural numbers has cardinal number Aleph Null. It is called an infinite set, and it is countable. It counts up to Aleph Null. Okay? So, for example, we're going to show that the set of multiples of 5 has cardinal number Aleph Null by establishing a one-to-one correspondence between it and the set of natural numbers. So we have the set of multiples of 5, 5, 10, 15, 20. What would be the general term for this set? Do you think it's 5n? Because if you do, you're right. So the set of natural numbers is 1, 2, 3, 4, etc. up to n. And we've put it in a one-to-one correspondence with the set of multiples of 5. 1 pairs with 5, 2 with 10, 3 with 15, 4 with 20, n with 5n. Pretty cool, right? Okay, show that the set of odd numbers has cardinal number Aleph Null by establishing a one-to-one correspondence between it and the set of natural numbers. So the set of natural numbers are 1, 2, 3, 4, etc. The set of odd numbers, 1, 3, 5, 7. The general term here is 2n minus 1. Notice the difference between the terms is 2. That's where we get 2n. 2 times 1 is 2. To get that first term, I have to subtract 1. So 2n minus 1 is the general term. And that's it. It's that general term that's going to trip you up. You need to practice that. So good luck. Email me if you have any questions.